Very good afternoon to all of us here. So we are moving on to the session 3 of day 1. So today we have Jespa Madam from Dan Sagar University, Bangalore. So she is going to take the session on artificial intelligence and machine learning in design and manufacturing. So let me invite Farnosh K. Francis for introducing the speaker.
Good afternoon, one and all. For the third session of day 1, we have a talk on artificial intelligence and machine learning in design and manufacturing. Today we have Dr. Jesma Balasanga Maheshwara. She is currently working as Associate Professor and in charge chairman in Department of Computer Science and Technology, Dan Sagar University, Bangalore. She is certified as an educator with Global Technology Literacy Competence by Microsoft Corporation under the UNESCO ICT framework. Dr. Jesma has received an infrastructure strengthening grant of rupees 20 lakhs from Vision Group of Science and Technology in year 2015-17 for setting cloud computing and big data research facility at Department of Computer Science and Technology, Atria Institute of Technology, Bangalore. She got the Microsoft Azure Research Award grant of $40,000 US in year 2014-16 from Azure Service to Atria Institute of Technology. She was also awarded as Microsoft Educator grant of rupees 10,800 US in the form of Azure Service for the year 2015-16 for effectively conducting big data laboratory equipments prescribed by Visvesvaraya Technological University for the postgraduate program for first-year students. She is also recognized as a senior member of ACM since June 2015 for demonstrating performance in the form of research publications that sets her apart from her ACM peers. Her research areas included distributed computing, data analytics. So I welcome Dr. Jesma Madam to handle this section.
Thank you, sir. Thank you, Shanmugesh sir, for this opportunity. I'll present my screen. Is my screen visible, sir?
But the sound is very visible. Can you increase the sound?
Yes, sir. I made it maximum now. Am I audible now?
Yes, sir.
Okay. So I'll be starting off with a quick overview of the industrial revolutions. Basically, what we'll be covering in today's session is I have 1.5 hours time. The first half an hour to 45 minutes is on the basics of Industry 4.0, and the remaining we'll look at the various tools and technologies that we can use to start learning artificial intelligence and how we can use it for the manufacturing industry, particularly Internet of Things and Industry 4.0. So I'll be very quickly going through these slides because I don't want to go into the history of industrial revolutions, but we should be aware of how the revolution is happening and where we are. So if we look at this, we are in the fourth industrial revolution, which started in the year 2015, and there's a question mark which is put here. So it may go up to 2050. So currently we are in the industrial revolution, which is called Industry 4.0. I'll be telling you what Industry 4.0 is. Basically, when we talk about Industry 4.0, it's a set of systems which are connected to each other and they can talk to each other. Now, the question that people may ask is, how is Internet of Things different from Industry 4.0? When we are discussing about Internet of Things, the emphasis mainly here is on 2 or more devices communicating to each other and taking decisions. Whereas when we talk about Industry 4.0, we are actually looking at the systems themselves being intelligent in order to perform tasks based on certain criteria or parameters. So machine learning, artificial intelligence, cybersecurity, blockchain, digital twin, all of these play a very critical role in Industry 4.0. If you just quickly Google, you'll also notice that we are moving from Industry 4.0 to Industry 4.5. So even that has started coming up. Very shortly, I'll be telling you what Industry 4.5 is. Okay, so we will not go into all of this. Very quickly, we had energy revolution and then improving logistics as part of industrial revolution 1760, and this was the traditional engines that we would look at. So when you talk about Industry 4.0, it is extremely inter and multidisciplinary in nature. So mechanical engineering and electronics and communication play a critical role along with the computer science and engineering. So if you look at this, it is basically more towards mechanical engineering, where you see a central steam machine. Then we moved on to the industrial revolution, which was in the year 1870, where you have electrical power in factories, and then came telephone, telegraph, and telecommunications, drilling, turning, uh, drilling, milling, all of that happened, petroleum. So this was the industrial revolution in the year 1870, and this is a classic example. So if you look at here, there are machines. Along with machines, you also see human beings, an assembly line of motors. Okay. So next, we will be moving on to, yeah, this is an example of electromechanical controls in a factory. So what was in the industrial revolution, second industrial revolution, was there were a lot of electromechanical components, and these components were heavily managed by human beings. Okay. So now we'll go to the 1970, which is third industrial revolution. So here is where basics of automation started. Feedback loop control, sensors and actuators, CNC machines, data logs, production history. So actually the information that these machines were generating were actually put into uh, a data log, and this data log was manually reviewed by humans, people, and then they would generate reports. So you had a lot of reporting which came into picture in 1970, which is efficiency, quality assurance. All of this was being done manually. And then finally, this is an example of industrial automation using PLC. A lot of academic organizations have these systems where, in the first or second year, mechanical children actually learn to use and develop simple basic models. Okay, so this is another modern PLC cabinets, and this is an architecture. I'll not be going detail on all of this. Okay, so this is the way things were set up. So if you look at the processes that they would design as part of third industrial the revolution, you had stamping, spot, vault, assembly 1, assembly 2, assembly 3, shipping. So this was an architectural diagram, and all these lines that you see, basically daily shipping plan. There was a lot of, again, manual work involved. But the best part of the third industrial revolution was whichever electromechanical components, they heavily used electromechanical components. In the second industrial revolution, they were a combination of electromechanical components and human beings. Third, they revolutionized in such a way that these electromechanical components were able to generate data and dump the data, and that was manually being analyzed. Okay, so what was the benefits of third industrial revolution over the second industrial revolution? It had improved productivity, product quality, cost reduction, because there was some level of automation involved, and it's still very heavily dependent on humans. And in what factors did it depend on humans? It basically depended on data analysis, production, control and planning, forecast analysis. All of this was being done manually by humans. Okay, so this is where there was a touch of computer science algorithms and methods, techniques coming into picture. Next, the industrial revolution started in 2015. Okay, so what is the scenario? This is basically categorized into four. First is the scenario, the level of customization, the technology is used, and moving forward, how the fourth industrial revolution will pave the pathway for industry 5.0 and continuing up to 2050 or even longer. Okay, so the era or the phase that we are in is actually the founding step, and lot of major MNCs have actually created lot of tools and technologies that we can ready-made make use of in order to build our own simple intelligent systems. So even that I'll be discussing. So coming to the scenario. So in 2015, we saw that there is a demand for highly customizable products, and these products have very short life cycle, and the market is extremely competitive, and we have a lot of environmental restrictions. What do I mean by environmental restrictions? Every other company, according to rules and regulations and norms, is expected to be environmental friendly, climate friendly. So these were the scenario in which we had to come up with a solution, which is what is called Industry 4.0. Now coming to customization, highly flexible production lines. It had to be productive and cost effective and make to order. What is the meaning of make to order? Make to order meaning to say that if I'm looking at a very different system which is not in the market and it is customizable to me, then the company or the industry should be able to provide a personalized experience to me. This concept of personalizing, where a product does not fit all the market, but my product, the same product is made custom made to me and maybe my friend, or we have different requirements. So that started coming into picture, which is customization. And the new technologies that came into picture is automation and robotics. Again, with AI, big data, cloud computing, and simulation. So all of these are buzzwords which all of us know: Internet of Things and cybersecurity. So we look at why industry 4.0 is so hot, because lot of countries all over the world are planning to invest lot of money into industrial revolution 4 and 5 as well. Okay, so the estimate here is to invest 140 billion euros per year by 2020. Okay, so now we'll actually look at what Industry 4.0 is. These are the pillars of Industry 4.0. So we have looked at first, second, third. We are here in the fourth industrial revolution. So the fourth industrial revolution is actually also termed as the cyber physical systems. So here is where you have smartphones, desktops, tablets, and machines, all of them talking together virtually and in a physical environment, and they all rely on each other. And there's a concept of security being built. So if I look at the vertical component here, it is the degree of complexity. So as we move on towards Industry 5.0, 6.0, 7, and all of that, the degree of complexity is likely to rise as compared to what was there in the previous revolutions. Okay, and this is known. So what is Industry 4.0? Industry 4.0 is a set of systems connected to each other, which uses various tools and technologies, including cloud computing, big data, artificial intelligence, cybersecurity, all of them, to solve a particular problem. They are basically electromechanical systems which are intelligent enough to be able to solve problems. So if I look at the kind of work that systems which form the part of Industry 4.0 can do, is let us look at the data analytics. If we look at data analytics, it can be categorized as the first one, which is descriptive analytics. The second one is um, prescriptive analytics. The third one is predictive analytics. So when we talk about descriptive analytics, it is the data which you can describe looking at the data. So there are a lot of packages in Python and R available through which you can describe the data. Now coming to prescriptive analytics. Before prescriptive, we have predictive analytics. What is predicting? You have historical data. Based on historical data, you actually land up predicting what will happen in the future. Next comes the prescriptive analytics. Prescriptive analytics, once you know what is going to happen, you take precautionary measures prescribed in order to prevent it from happening. That is intelligent decisions. So that is where Industry 4.0 comes into picture. It heavily relies on prescriptive analytics. Okay, so this is a nice picture on Industry 4.0. So if you look at what is very different in this picture, is that these machines are intelligent machines, and this is a pipeline, an assembly of devices which are moving in this on this rail, and these are already made, but these systems are so intelligent that they are, there are cameras here. They look at it, identify the the parts which are have bugs, or which is not functioning properly, or which has to be repaired, and then they go ahead and do it. That means they are more so human-like, these systems. And this happens in a pipeline. So this is a classic example of Industry 4.0. So they decide, now this may look very simple, but if you look at it from a very high level, this is a big tray that you see here with lot of holes and a lot of hardware and mechanical components. Where is the place area within the system where there is a bug or it requires fixing? It's not done by humans, it is actually done by machines. So if you look at this entire picture, you hardly see any human being. There's not even one that I could locate here. Okay, it's all done by machines. And if you look at here, if there's nothing wrong here, then these systems don't do anything. And whereas when you look at this, there's anything wrong, then they start fixing it. So that is how did this happen? How does the machine know that there's a bug here and not here, and this part is correct? So this is what Industry 4.0 is all about. So there is this nice video. We'll be watching it after some time about what Industry 4.0 is. So we look at what are the components, what makes up an Industry 4.0. First one is autonomous robots which move around and go about fixing things. You have industrial internet, which is these robots speaking to other robots through the industrial internet. Then you have addictive manufacturing, simulation. You have AutoCAD and all of these tools to simulate. Cybersecurity, that means the robots and the industrial internet cannot be hacked. So make use of concepts of cybersecurity. Augmented reality. Now people can ask me, why augmented reality, man? Augmented reality is basically, if I go back to this picture, now as a human being, I don't have to be physically present here in this system to, in this place to keep monitoring if these devices which are in the beside the assembly are working correctly or not. All that I need to do is, if I have a simulated environment of this on my laptop, I can actually monitor it sitting at one place, or I can be in other room, and through the augmentation I can actually monitor and make changes to the way these systems work. So there is this concept, there was a project done at our university which was guided by our dean. I'll just give you an example of how augmented reality was used in the industrial Internet of Things. The Nokia factory in Chennai, which is near Chennai, they have a system similar to this. Now, what was their requirement is, there's a lot of they say this is not a very safe place for humans to repeatedly be there because there is so much radiation and all of that. So they wanted to monitor this through a virtual bot. That virtual bot will exactly look like this, except that it can be seen on a mobile device or a laptop or on a desktop, or it can be projected on the screen, and I can actually turn and mold my use finger recognition to move the devices, and whatever I do here in virtually, same thing happens here in reality. So that is where augmented reality, virtual reality comes into a picture. And of course, software integration, the data is on the cloud, and then big data and analytics. So where does AI come into picture here? Artificial intelligence, deep learning, machine learning, analytics, all of that falls under big data analytics. Why under big data analytics? Because for any system to be intelligent, it has to have historic data, and based on historic data, future decisions are made and verified. So these are the various technologies that is used under Industry 4.0. Okay, so now we'll come to the concept of artificial intelligence. So before I move on to artificial intelligence, we need to understand what is data analytics, what is machine learning, what is deep learning, and what is artificial intelligence. So data analytics basically is, you have a set of data and you derive meaningful information from the data. That is basic data analytics. It's a subset of data science. Okay, now coming to machine learning. Machine learning, you have fundamentally, it is categorized as supervised and unsupervised learning. In supervised learning, you tell the machine what it has to do. In unsupervised learning, machine learns eventually as to what it has to do. So now When you look at artificial intelligence and deep learning, it is under the category of unsupervised learning, wherein looking at the data set, you start, the system starts generating results by analyzing the various scenarios and coming up with a solution. So the concept of optimization problems is heavily used in artificial intelligence. Okay. So now coming at the various categories again, wherein we can begin with artificial intelligence. The first and foremost beginning step to AI is starting with machine learning. So what are the examples of how AI is used in Industry 4.2? When it comes to machine learning, failure detection. So detecting a failure, whether the failure is there or not, binary classification, predictive maintenance, data analysis, augmented reality, quality control, pattern recognition. So all these are some of the cases where machine learning is used. Going to the next level, multi-agent robotics, logistic robotics. So we have this concept of logistic regression. So there are logistic robotics. Again, this is a nice video which is just for a minute, which we'll watch a little later. Next is constraint satisfaction problems, operation sequencing. What is the meaning of operation sequencing? So if you look at here, there's a classical example where the operations are executed in a sequence. So there's a pipeline of operations which is actually happening here. So, and what are they? Materials and machines, available market, demand, inventory, allowed. These are some of the examples of how you organize the operations in sequence. So these come under the category of constraint satisfaction problem, which is again under artificial intelligence. So now we look at an example of a digital twin shop flow. Okay, so we'll go deep into this architecture. So like I told you how various technologies are used here. You have a shop floor service system. Okay, so if you look at what all is there inside, you have supply chain management, customer relationship management, enterprise resource planning, PDM, PLE. This is the actual physical shop floor, where there are some 3, 4 humans, and these are some systems which are connected to the internet, and there is this vehicle which is there also, and all of these are connected to the internet. Now, for this physical shop floor, there is also a virtual shop floor. So what is this virtual shop floor? That means all of these people are remotely able to control the physical shop floor. And how is this happening? This is happening through the concept of a digital twin. What is a digital twin? It is a digital twin of an actually physical store. So this is the way it is represented. So you have data, and then data. So data from all the three, the service system, the physical shop floor, and the virtual shop floor is getting stored in the shop floor digital twin. And in turn, what is the digital twin doing? It is doing only one thing, which is driving. It is driving all of this together. So here, if you look at it, there is interaction both ways. Here also interaction, and then you have the iterative optimization, interaction and mapping. So this is a classic example of a digital twin. So the question here is how to optimize production and decisions in unexpected situations through intelligent computation. How do we do that? How do we create a virtual environment integrated to a physical production and management system? These are very two critical questions to which we'll be looking at real use cases and how we can actually go about solving the problem. How do we actually design systems like this? What technology should we use? What tools should we use? What is the programming language required to even go about building a virtual shop floor or for a physical shop floor? We look at simple use cases. Okay, so we'll not go into the architecture of it, but we very quickly, I'll not take more than 30 seconds. You have pre-production, production, post-production, orders transmitted, real-time data is recorded, and finished products outputted as registered. So the architecture of the digital twin shop floor is categorized into pre-production, production, and post-production. So this is a very big, again, before production, during production, or after production. This is a flow chart where the yellow color represents the physical shop floor. You have the blue colors representing the virtual shop floor. There is simulation, predefined production, and all of that. And shop floor service system is by this color. Okay. Now we look at, this was both these two were on the planning phase. In the planning phase, you have three categories: the physical production, production, and post-production. And this is a high-level view of how the digital twin shop floor is likely to work based on these three categories, the architecture of DTS. Once the planning is done, once the design is done, then they start with the implementation. So next couple of slides will be looking at how exactly this can be implemented. Okay. So now looking at the implementation, we have the physical shop floor. So what components are used in the physical shop floor? If you look at it, you have sensors, automation, embedded modules. All of these are things that children learn, I mean students learn in their electronics and communication engineering. Generate and integrate data. Now recently MATLAB has gained a lot of uh, scope when it comes to electronics and engineering. Okay, so this is the physical shop floor is driven by basically electrical and electronic components. Okay, now coming to the virtual shop floor. So what systems are used in the virtual shop floor? Gather data from CAD, CAM systems. These are things which mechanical students learn. Simulated systems, management systems, able to translate 3D drawing into CNC code. Simulated production, sequencing it through virtual copies of actual operation stages. Constantly updating the information received from PS. So if you look at the virtual shop floor, it is more so designed for mechanical branch, and this is what they learn during their curriculum. Okay. Now the next is service system and digital twin data. So what does this part do? It provides data to both the physical shop and the virtual shop, as well as receives data from both, generating fused data, converge all of the data received from real production and simulation. So if you look at the concepts that we'll be making use of here, is more so of data science concepts. Okay. Now, when it comes to converging, you know, of all data received from real production and simulated, we'll go deep into what are the concepts that we'll be using in turn. So convergence between virtual and physical systems. First is Internet of Things, collecting and providing data. You need cloud computing because we are dealing with big data, which enables big data. And when we are talking about big data, these are compute intensive. When we are doing analysis on big data, and AI is the backbone of artificial intelligence is neural networks. And whenever we have a neural network, we look at what are the different layers of the network that we have, and to what extent the weight should be modulated, and how many layers and how many iterations should the neural network learn. So this cannot happen on a basic system. So that is where edge computing comes into picture and powerful cloud systems come into picture. Quick reaction regarding planned and actual protection. And this is where if you have to react, it's purely AI based. Real time decision making through data analysis. And then of course, when all of this is happening, surely I do not want the data to be manipulated. So security again comes into picture. So modern industry based, highly connected cyber physical systems. So when we are talking about convergence, which is service system and digital twin data, we have all of the latest trending technologies that we will make use of. And this is what makes it Industry 4.0. And if you look at Industry 3.2.1 previously, they didn't have this in a picture. So now if I look at going back and look at Industry 4.0, I cannot say Industry 4.0 is only computer science related concepts. I cannot use electronics and communication engineering concepts. I cannot say it is only mechanical related. So when we're talking about Industry 4.0, it's only mechanical engineering students or faculty who have to learn Industry 4.0. I don't think electronics and communication engineering or computer science and computing engineering faculty or students should not learn. So this is actually extremely multidisciplinary, interdisciplinary in nature, Industry 4.0. So children from these three branches and faculty from these three branches should come together and work when it comes to Industry 4.0. Okay. So now, till now we were talking about cyber physical systems. So we'll look at what a cyber physical system actually is and what are its components. So security in cyber physical systems, sensors and machines communicating, data in shop floor. We know how easily data can be hacked. So that is where cyber security comes into picture. Integrated supply chain. So what is a supply chain? Supply chain is a set of processes wherein you try to meet the customer demands. There is data flowing between companies. If I have to take a simple example of Amazon, which is an e-commerce which heavily relies on intelligent supply chain management, when I place an order for, let us say, to purchase a pencil which costs around 10 rupees on Amazon, then the cost of the pencil, 10 rupees for one pencil may be very costly. So maybe I'll get a bunch of 20 to 30 pencil, a pack of 20 to 30 pencils for 10 rupees. Now we need to understand how exactly does Amazon internally work it out. Is it that the Amazon has connections with the nearby store where this sack is available for 10 rupees and they deliver it, because delivery charges, transportation, logistics, all of that again is incurring, which has to be taken care by the person who's actually delivering it. So integrated supply chain, data processing between companies also plays an important role. Again, there is data here which needs to be secure. Project and processes footprint. So this is an extremely confidential data for somebody. Somebody knows this is how the entire production line works, then I can actually hack into this soft copy and make any changes. Instead of this arrow going from here, from this to this, if I change it from this to this, because it's a simple example, the actual production systems, the flow chart are very complex, and it spans several pages when a printout is taken. So anywhere in between change is made, then it becomes very difficult for people to verify, and the entire processes gets changed. So it becomes very easy for hackers to make such small changes, which to me I may not be able to identify, but it does create havoc. So going back, projects and process footprints, which are very confidential in nature and should not, and fraudsters should not get access to it, and of course sensitive information. So what is the estimate? It's estimated that the number of connected devices will increase to 14 billion by 2020. Okay, so which is a great risk of cyber attacks. So it is heavily risky for cyber attacks. And the best part is in India, when we look at the states, the recent statistics indicated that Karnataka tops the highest when it comes to the number of cyber attacks. Okay, so now we look at how manufacturers are moving from closed systems into IP-based cyber systems. So when we're talking about closed systems, that is what was Industry Revolution 3. Now we are basically moving towards IP-based cyber systems. So Industry 4.0, the other name also is cyber physical systems or IP-based cyber systems, which is IoT, highly connected, highly cyber vulnerable. Hello. Varan has to mute. Okay. So coming back. Okay. So this is a very high um, architecture of how cyber physical systems look like. You have again applications, IoT business processes, virtual entities, IoT services, communication. All of this comes under the management layer, sensory layer. IoT virtual IoT process management services comes under service organization, and all of these talk to each other through the devices. Okay, so this is how there is this layered architecture given for security in cyber physical systems. Okay, so this in the year 2014 in US Industrial Control System Cyber Emergency Response Team, there were security issues reported as 245, and we know to what extent it has increased now, 40 billion by 2020. So this is an example of what happened in the year 2014. So if you look at this slide, you will understand that they had actually started discussions in the year 2014 on Industry 4.0, and actually Industry 4.0 came into picture in the year 2015. Okay, so continuing with security in cyber physical systems, autonomous protection through artificial intelligence. So we again make use of artificial intelligence for various things, even to make the system secure. They make use of the concepts of AI. AI systems are meant to be already used in cyber systems for optimized protection. The data, big data that is produced by the industry, and we use data mining concepts to detect that hack threats let digital footprints. So that means whenever you start hacking a threat, it actually leaves behind a digital footprint. Okay, and the basic quality of service requirements that we are looking at here is faster response and protection. Protection. Okay, and there are couple of other ideas. Now, the very nice thing about this is bio-inspired adaptive manufacturing. Okay, still now we were only looking at three fields, branches coming together for industry 4.0. First one is computer science, electronics, electrical, and mechanical. The next level that they're going ahead with is biology. How you can put in bio inspired adaptive manufacturing into industry 4.0. So this is a very high level overview of how they want to come up with robots which are adaptive in nature, at the same time inspired by biology. So you have central controlling providing demand and cost effective analysis, distributed controls, and using genetic algorithms into the manufacturing. So when we talk about genetic algorithms and bio-inspired algorithms, there's a lot of fundamental research being done in these areas itself. Okay, so this is about the uh, you know strategy to industry 4.0 and an introduction to industry 4.0. So before I go to this slide, which has around 28, I would like to go back to how we can start using industry 4.0 and what are the systems. So I'll be making you go through a series of links that I have opened here for you to understand who are the players in industry 4.0 and industrial internet of things. So we'll be taking four major players. All of us are aware of Amazon and Amazon Web Services, which is the cloud platform offered by Amazon. Next, uh, we have Microsoft. Microsoft provides its cloud platform called Azure. We also have IBM. IBM has its own, intelligent system called IBM Watson. And then, of course, the fourth one is Google Cloud. So these are the four major component industries, major MNCs, which play an extremely important role in making industrial 4.0 easy to us. So one of the complicated challenges that we academicians basically face is, we cannot be master of all. Now, I cannot be a mechanical engineer and an electronics engineer and a computer science engineer, a big data expert, AI expert, a machine learning expert, cybersecurity expert, intelligent manufacturing expert. For me, it is next to impossible to know everything. But when it comes to Industry 4.0, what is important is connecting the dots and being able to come up with a system, being able to quickly deploy a system which is able to, do things which an intelligent robot could do. When we're talking about an intelligent a robot, it is not a bot which picks up an apple from here and drops it there. No, that is not industry 4.0. So what is industry 4.0? If I have to give a very basic hello world example to industry 4.0, it may be that there is a robot which picks the apple, goes to the farm and identifies that that is the apple, and the instruction given to it is, deliver the apple, green apples to me. It will go identify different colors and pick a green apple, come back, check if the apple is okay, and then put it into there's another robot which puts into the box, another robot that packs it, the other robot knows where to deliver it to which address, and then the delivery happens. This is a pipeline of series of instructions which all happens automatically without human intervention. And that is industry 4.0, if I have to give it as a simple example. So it's a combination of electronics, mechanical, and computer science and engineering. Where does intelligence comes into picture here? The first is the robot being able to identify that that is an apple. Apple is a fruit, and there can be mangoes, oranges, and all of that in the farm. It can only identify apple, and then being able to differentiate that the instruction it received is that it should only pick green apple and not red apple. And then furthermore, going ahead. So that's the classic example. So we'll look at how exactly as academicians and people who are just stepping into working on industry 4.0, how can we go about even designing simple basic systems, and what tools and technologies we need to use. So we'll start with Amazon. Okay, Amazon provides a lot of services and products on its Amazon Web Services for Industry 4.0. So there are businesses which are using Amazon Web Services in order to connect to the cloud and making use of Industry 4.0. Okay, so this is a nice example connecting disparate industrial systems to AWS using Ignition Edge. Okay, and this is another example. I'm just very quickly going through these examples because I have so many of them to cover. Later on, you can just Google. I'll also share you the URL. Industrial IoT, from condition-based monitoring to predictive quality to digitizing your factory with Amazon Web Services IoT services. Okay, so what is it that they're telling? What is the meaning of digitizing a factory itself? When we talk about digitizing a factory, it means to say that all the equipments that are present in the factory, the units that are present in the factory, I'm able to actually remotely access it, or I'm able to remotely monitor it. What is happening? Industrial IoT, which is termed as IIoT, which is Industry 4.0. It actually is bridging the gap between industrial equipment automation networks, usually called OT, operations technology, and information technology. So, what is happening in this post, which talks about from condition based monitoring to predictive quality to digitize your factory with AWS IoT services, is a classic example. And if you look at the date that it was published, it was 07 April 2020. So, and what are the keywords? AWS green grass, AWS IoT analytics, AWS IoT platform. So, what is it that they're doing? Data is collected too infrequently, data is difficult to access, unable to overcome data loss and link data together. So, these were the challenges that the company or the factory had, and that is what is being addressed using AWS. So they have given a nice example, the automation pyramid according to ISA 95 model. It's from ResearchGate. Level 1 is production process, level 2 is sensing and manipulating. Sorry, level 0 is production process, level 1 is sensing and manipulating, level 2 is monitoring and supervising, level 3 is manufacturing operations, and level 4 is business planning. So this is all in seconds, this is milliseconds, seconds, minutes, hours, days, months. It all gets over in a couple of months. Okay, so how does it work? So we'll take an example. AWS Internet of Things helps industrial companies overcome challenges to attain business goals. And how is AWS doing that? Through its components called Internet of Things. So whatever are the things that we call, which have to be connected, which becomes the Internet of Things, they all can talk to each other over Amazon Web Services. So firstly, Amazon Web Services, I'll be going in detail, and the other examples that I'll be going through, I'll be giving a very quick overview, because here is where we understand the process flow. Amazon Web Services lets you easily connect, manage, update devices of any type, And what are these devices? It can be small microcontrollers, or you can move up to powerful gateway devices. You can also have programmable logic controls, SCADA, supervisory control, and data acquisition systems. So all of that, billions and millions of devices are supported by Amazon Web Services, which can all get connected to each other and form the Amazon Web Services Internet of Things. And the best part is Amazon is giving teachers and students free access to its Amazon Web Services, which we can apply and easily get access to. Okay, so this is a nice reference architecture. We'll not go into detail. There is this example use cases, asset condition monitoring. Traditionally this was done by humans, predictive maintenance. So the person had to walk around factories and check whether the equipment is working, not working. It should be maintained and call the maintenance manager. Predictive quality, all of that was being done, uh, manually, and now all of them can be automated using Amazon Web Services. Okay, so for each one of them, they've given a example. So operations technology, Amazon Web Services IoT core. So this entire module talks to the IoT core, gives you analytics, and there's an IoT shadow, and then this is AWS IoT Green Grass, which is a framework, and this is how it goes through. I won't go in detail. There's this concept of edge computing also, industrial Internet of Things design pattern. You have extract information, transform information, load information, protocol conversion, data rate, polling versus events, transform. The formats is from CSV, comma separated, comma vector separated to JavaScript object notation, filtering, data transmission, buffering, compression, gateway to the cloud. So Amazon Web Services IoT Green Class doing local processing of IoT data. So predictive maintenance and predictive quality. Okay, so this is one example that I took. There are several other examples that I have given on the blog of Industry 4.0 under Amazon Web Services. So it becomes very free. We all can create a account, Amazon account. I think for 1 year, a very basic instance is provided free of cost, and then we can actually start creating our own simple IoT system. We can actually simulate a simple IoT factory, and then virtually create a digital form of the factory and do some case studies or using Amazon Web Services. Okay. Okay, this is a success story by a connected factory solution based on Amazon Web Services IoT for industrial success. So unlock data to modern manufacturing. You have enterprise level visibility, the manufacturing challenges, and all of that. So we'll not go into detail. So now this is the web page where you have industrial Internet of Things. And what does Amazon actually bring in? It can gives us uncovers deeper insights from your data and build rich and scalable industrial applications using Amazon Web Services IoT. This is really awesome. When it comes to student projects, you can actually have a student account, a teacher account opened on Amazon Web Services, and use the services, industrial Internet of Things services that is provided by Amazon to build simple systems which can actually be scaled. So when we look at my own university example, a lot of children are making use of the Amazon Web Services Internet of Things to actually model traditional factories and actually make them digital factories. It's as simple as that, and it can be scaled because whatever features, tools, and technologies that we use on the ones that I just listed, all of them are actually very scalable. Okay, so there are use cases. We already saw this, and we have major players: transportation, energy, manufacturing. Okay, so what all is Amazon basically providing? You have complete solution for industrial IoT. What do I mean by complete solution? Amazon Web Services IoT is a set of fully managed services that makes it extremely easy to deploy and manage a complete industrial IoT solution. There has been some cases where, with a little bit of learning and experience, we can have a complete industrial IoT solution being set up in as less in 1 or 2 days. And security designed for IoT, massively scalable, and you can also analyze and collect to analyze data. So this is about Amazon Web Services. Okay, now we look at Microsoft. Microsoft uses Microsoft Azure platform. So it says factory of the future today. Keep pace with rapid changes of Industry 4 by modernizing your factory with new disruptive technologies. And what are those new disruptive technologies? It is augmented industrial automation, software with Internet of Things. All of this is provided by Microsoft. Cloud-based computing, artificial intelligence, and mixed reality to drive new levels of productivity and innovation. There is this ebook that you can download from here. That is how it works. Connect people with processes and products. Boost employee and manufacturing productivity by integrating people with intelligent mixed reality devices, industrial IoT enabled machines, and AI enhanced applications. Okay, so it's called the intelligent edge. So they have again given a very nice example of how Jabil is creating their factory of the future, improving precision in machine failure prediction. See how global manufacturing services date. Jabil predicts manufacturing issues in real time and takes action before failure occurs. by analyzing billions of data points across multiple machines. So again, if you look at here, you find humans and all of that, but it is an intelligent system which is able to improve the precision in machine fabrication. And Amazon also gives you the Azure IoT connected factory. Okay, so this is about an example of Microsoft Azure. Again, Microsoft Azure has provisions for teachers to request for credits to access Microsoft Azure and then run simple industrial IoT experiments on their platform. Okay, so next I'll move into Google Cloud. Google Cloud also provides industrial Internet of Things, accelerate business agility with IoT data from your physical systems. Okay, so what is Google providing? Smart cities building, real-time asset tracking, again predictive maintenance, logistics and supply chain management, cloud Internet of Things with our ecosystems, and all of these are examples. Okay, Microsoft provides you something called as the Azure IoT Hub, and there's this button which says start for free. They give you some free credits where I can explore the Azure IoT Hub. And what does this IoT Hub do? Manage service for bidirectional communication between IoT devices and Azure. Okay, so these are some of the features that they have, and uh, this is a video that they've provided which actually shows you how to go about coding it on Microsoft Azure. Build and run hybrid Internet of Things apps across data centers. Azure Stack Hub is an extension of Azure that provides a way to run apps in an on-premises environment and deliver Azure services in your data center. Okay, there's a video that you can watch when you go to the Microsoft website. Okay, now we'll move on to IBM. So what does IBM do with Internet of Things and industrial IoT? So again, on IBM, you can get started on the IBM Cloud free of cost. So you can connect your device, send data to the IBM Cloud, set up and manage your devices, and use APIs to connect apps to your devices. These are all the IBM Watson IoT platform. See what all IBM Watson can do, IoT solutions, the products, all of this is given by IBM. Okay, so this is an example of a combination of manufacturing operations and management solutions that IBM is providing. IoT and AI are enabling a new surge of manufacturing productivity with Industry 4.0. So we'll have a look at this IBM research, Think Lab, Cognitive Manufacturing, which is just 1 minute 54 seconds.
Intersection of innovation in the marketplace.
The focus of our department is to build an analytics to help industrial companies.
So there's the whole range of what we can do with mobile, with analytics, with cognitive, with workers, all the way up to the machines they operate, all the way up to the plants, and how to make them run better. We've been able to develop mathematical methods that are much simpler and faster to develop reliable monitoring protocols. So we've been able to dramatically reduce the amount of time and the amount of engineering activity required to develop models that will reliably tell us when one of these tools is behaving in some sort of aberrant fashion.
We developed a cell monitoring system where the receive the sensor data from cell engines. We applied a similar mathematical technique, and basically our mathematical algorithm was proven to be better than experts' methods.
I think we can actually transform the practices of the industry today by bringing data as a resource to decision-making of our projects. So essentially what this will do is it will augment the decision-making process, which is based on experience today, to help it along with predictions that come from an understanding of what happened historically with
all this stuff we keep talking about are feeding into our making our factories, our manufacturing, our mining operations, generally production, much more efficient.
Okay. So this is the IBM research think lab cognitive manufacturing that we just saw, and we also saw how multiple things are being used simultaneously. So I'll close this. Okay. So so there are some knowledge and solutions provide. Again, IBM has credits for faculty members. Okay, so this is about the thing, and this is one nice website which actually combines some basic experiments on artificial intelligence, Internet of Things, big data analytics, mixed reality, robotic process, cybersecurity, edge computing, and all of that. Now, going back to my presentation, before I would like to continue, is there any questions that I can take? Please let me know. You can, mention your questions in the chat box, that I'll be happy to answer.
Any questions from the audience?
Okay, I think you don't have any questions, so I'll proceed. Okay, so now what we'll be looking at is the next part. What we basically saw till now, a brief overview is we looked at what is Industry 4.0 and how we had the Industry of Revolution starting from 1 to 4, and we looked at what are the tools and platforms that we can use for Industry 4.0. Okay, so now here we will look at a specific case of how to use artificial intelligence. What are the sample artificial intelligence? What are some sample applications? More specifically for the manufacturing domain, how we can use AI in planning and how we can improve manufacturing with data and extracted knowledge. Okay, so the resources for this is AI, the topics that is being taken, and then there is this Wikipedia on artificial intelligence, which is written by Russell and Norwick. Okay, so all of us know what artificial intelligence is. They are basically intelligent agents which are used to build useful systems. We talk about symbolic, which represents logic, reasoning, and search, and statistical, which uses machine learning and Bayes rules, and also cognition, which tries to understand the working of the brain. So there are a couple of videos and chat with Ramona, which we just saw, IBM Watson, on how IBM Watson makes use of AI, and some dance moves by Asimo on the area. These are some of the sample AI systems. Okay, so there's a list of applications of AI in lot of areas: assistive technology, automatic programming, autonomous vehicles, banking, finance, all of that. What are our focus is basically on automotive industry. Okay. Okay. This is by IBM, this content that I have taken. So we'll first look at an overview of what a software system is. This is by IBM Corporation in the year 2014. Okay, software system. When we talk about a software system, we have a reference data, then we have a business process logic. We read the input and process the output, and then we have the environment. So this is what makes a business logic to declarative data. Okay, so now we'll look at an example of taking care of a baby, individual's extension. This is without using concepts of AI, and this is using concepts of AI. So you have an agent here which is attempting to be an intelligent agent, and expected behavior that that we're looking at: inform, alert when, crying, alert when, awake, alert when, idle, do, raise temperature of the room, play music. So what is it that we are doing here? Inform and do. So when we talk about predictive analytics and prescriptive analytics, the do part, raise temperature of the room, play music, all these are prescriptive. Based on what conditions? When the child is awake, crying, all of that. So this is an example of an intelligent agent. Okay. Now the same example of artificial intelligence when it comes to assisted cognition. Again, they have given an example. Send body temperature, body parameters periodically. This is what it has to do. And expected behavior: alert when idle, alert when away from known location, alert when checkup medicines are due. Again, this is a example. So now, keeping these two examples in mind, we will look at how we can arrive at the expected behavior, which is inform and do for industry 4.0 applications. So I'll look at some of the applications here. So I'll go to a platform called Kaggle.com. Kaggle.com is a data science platform which was recently acquired by Google. So here we get data sets which we can use to analyze things. So I'll click on data sets and I'll search. Maybe I'll be more specific in my search. Okay. So I'll open a couple of these data sets. We look at what kind of data actually is dealt with in industrial Internet of Things. So we will not look at discussions. I am more so specifically looking at data sets. Okay, so we have these two data sets that I'll open. Fine. Industry 4.0 or Industrial Internet of Things. Okay, so we look at temperature readings, IoT data, relational data set from IoT devices to record temperature readings. Okay, so this is about context. Industrial Internet of Things 4 is coming to cover all enterprise monitoring and maintaining systems. So we need bold and sustainable algorithms and approaches to analyze the IoT sensor data and find hidden patterns and insights. So there is this data on heat index, which contains temperature and humidity, is one common data recorded on these IoT readers. The frequency of the upcoming data is very fast. The sensor reads hundreds to millions of data per second. There is huge and versatile application of this data in real world like agriculture, weather forecasting, soil monitoring, treatment, enterprise, and all of that. So we look at an example of the data. So what is this data set contain? It is 6.63 MB of data, and these are the parameters. So I look at the column. It has a unique ID for each reading. You have a room ID. Room ID is in which device was installed, inside or outside. Noted date, date and time of reading, temperature readings, whether reading was taken from device installed inside or outside the room. Okay, so these are the data. We also have a lot of code. We can download the data set from here. A lot of code which is also available. So what is a notebook? These are the tasks. Task is what was the variance of temperature for inside and outside room temperature? A question. There are 3 submissions which were all accepted. Predict the next scenario. 2 submissions. How outside temperature was related to inside temperature? 5 submissions. Okay, then you have notebooks. So these are all example codes which are available for us to do some basic analytics and run some basic experiments to understand the temperature sensor that was installed in the enterprise building room. both inside and outside the building at random intervals. That means the temperature was recorded inside and outside the building at random intervals. The recording say speed was per second. So every second the temperature was recorded. So we know the data set details, which we already went through. The tasks completed is variance of the temperature and how outside temperature was related to inside temperature. Okay. So now this is the code. We will not go through the code. We have read the file, read data files and provide insights. I'll just at a very high level go through what the code is doing. First 5 rows, last 5 rows, then shape of the data, unique values, information about the data, memory usage, the description. I spoke about descriptive analytics. Then what data analytics has been done, missing values, separate date and time. Let's separate date further into days, months, and years. Reassemble whole data frame and print the new data frames. Then they're visualizing the data. These are some of the basic analytics that they have done. So this is exploratory data analytics, and of course the two tasks that was mentioned. Okay, so this is on EDA, on exploratory data analytics, on temperature reading IoT devices. Okay, so now we look at the next one, which is IoT temperature forecasting. So here is where some machine learning algorithms are made use of. So we'll just quickly go through this. So the best part of Kaggle is that I can register, then sign in, create a new notebook, download this code on my notebook, run it, and save it. So the Kaggle is actually under Google. The best part is for a lot of teachers and students, it becomes very easy for us to go about with, practicing uh, basic programs on analyzing IoT data very easy. And the best part is I don't have to have a complicated, high-end laptop or desktop to even run these codes. Kaggle actually provides us with a virtual interface. So this new notebook, when I create, it has the potential to run the code. Of course, there are limitations, but all that I need is maybe, I can also use my mobile phone and run these methods. How that is, everything is taken care by Kaggle. Okay, so I don't need to have a high-end laptop to run these codes. It actually provides a interface to execute and run the code right inside the notebook. So now we look at IoT temperature forecast. So what does this contain? Project details, goal of this notebook, how to import libraries, how to load the data set, pre-processing, date time information, seasonal information, timing information, unique identifier defined. All of this is code. When you talk about exploratory data analysis, univariate, multivariate, time series analysis, how is the data modeled? Data preparation, building the model, predicting future temperature, conclusion, task submission, references. So the project overview, we already know that we have temperature data set from inside and outside the building. The data set details are known. Goal of this notebook that all of us can use and practice is practice data cleaning technique, practice EDA technique to deal with time series data, practice visualization, practice time series modeling data. And the Python library which is used is Profit. This is a library I think given by Facebook. Okay, so this is again the code. Very nice. See, right here I can click to get the output code. This is the code output. You can actually clone this and then go about running it. Seasonal information: winter, December to February; summer, March to May. We create seasonal variable based on month variable. So they've also given a reference to from where which notebook came and who's the author for this. This is the author, Cohen, who's a Kaggle expert. He's from Tokyo. He's a data scientist engineer. So once I log in, I can also follow him for his future notebooks that he's likely to put on Kaggle. Okay, so you have input, you have output, you have code, everything is available here. So this is time series forecasting. We look at what kind of forecasting techniques were used. Univariate, multivariate. Code is here. You just have to click on the code and we get the globe. And this is the graph. Time series analysis. Modeling, data preparation, building the model. This is the prediction. Conclusion. So I'll read through the conclusion. ID column was not used as useful information, but it was used as a unique identifier for each row. We have got some useful information such as seasonal information or timing information for analysis from date time column. Inside temperature is composed of a single distribution, while outside temperature is composed of multiple distributions. So these are some of the conclusions that the person was able to get from this data set. Okay, so I'll go through one more. Device not required. Data health checkup, visualization, classification. So this is about one data set. Likewise, I'll quickly go through the other two also. This is CNC mill toolware, variational CNC machining data. So we look at the data. This is the data. You have all these experiments, up to 18 experiments. There are totally 21 files and there are 871 columns in this data set. This data set was uploaded in April 2018 by CNC Milling Dataset, University of Michigan Smart Lab. A series of machining experiments were run on a 2 cross 2 cross found 0.5 wax blocks in the CNC milling machine. In the systems level manufacturing. So you can go through this. The data set can be used in classification studies. You can use this for toolware detection of inadequate clamping, and what are the inputs? Number, experiment number, material, feed rate, clamp pressure, and what is the output? Tool condition, machining completed, past visual inspection. Okay, time series data was collected from 18 experiments. The features available in the machining data sets are, all of these are the features, which are nothing but the input components. And according to what they've written, there's 871 columns. Okay, fine. So we have got a fairly good idea on what the data set is. We'll look at one sample data set maybe. Okay, so this is how the data set looks like. These are all the columns, details. Row 1, row 2, row 3. So you can go on. You can also download the data set from here. Okay, so we'll look at notebooks. There are 8 notebooks. Predictive analytics in manufacturing, CNC milling. There is some outlier detection work that's being done. XGBoost algorithm was run. Then there's a decision tree algorithm. And there are some discussions. Okay, so this is about CNC mill. Now we'll come to versatile production system, data for condition monitoring, predictive maintenance, and machine learning. Okay. If you can see the results from data taken of VPS, which is part of Smart Factory OWL, the VPS was used in previous research projects, for example, Improve. So we can go through the products and look at the CSV files. You have delivery module, dosing module, filling, cap grabber, and all of these examples. So this is how the data set looks like, and what are the columns? You have silo full, silo min full, aspiraton, so all of the example of what this is also given. So we look at some notebooks analysis that is done on this data set. Okay. Industrial IoT digital twin, categorical data using EDA. Okay, so these are the 2 notebooks which are available. I'll just quickly pick one and we'll go through the code. You have report, This is the flow chart, modules, correlation, what if. I'll directly go to the code. So this is the code. This is the output. Log. Who's the researcher? So again, he's a Kaggle master. He's from Paris and he's an engineer. Okay, so going back to the presentation, so we have seen some examples of analytics on data set from the manufacturing industry. So now we look at what an intelligent agent is. When we're talking about industry 4.0, it is all about intelligent agents. So what is an intelligent agent? An intelligent agent is software that assists people and acts on their behalf. Agents can help people and processes. Agents are used for automation and control. So filtering information, fixing problems, automating complex procedures, and so on. Okay. So this is a example of a planning, a classic planning. So you have a state, you have an action, you have a goal, you have an environment, static, observable, deterministic, what action to take next. So this is an example of a simple planning. There are two states, initial state and the goal state. You have a robot arm, the blocks world. These are the blocks. The states are represented as on table 1, table 2, table 3. The action is pick up a block by a robot. What is the precondition? It should be a clear block. Arm empty robot. On the table, place the robot. Add holding block. That means the block should the robot should hold the block. Okay, and there should not be any block below. That means it cannot place one block on the other. So this is a representation of an example of a simple agent and the pipeline process. So this is planning. I'll not go into detail on all of this because this requires some fundamentals to be understood. So I think I will um, stop at this and let me know if you have any questions. Okay, no questions. Sir, Shanmugesh sir,
Yes,
and
ma'am.
I'm done. Yes, thank you, sir. I'm done.
Okay, ma'am. Thank you very much, ma'am. Any queries from the participants? Participants, any queries?
Yeah, am I audible, sir?
Yes, sir, you're audible.
Ma'am, I understand the Industry 4.0 contains very many elements or components. And can you throw some more light on augmented reality? That is very important in this. Yeah, please.
Okay, so maybe I can show a nice video. Maybe I'll share it along, sir. There are these two concepts, these two disruptive technologies called virtual reality and augmented reality. So what a virtual reality is that you're actually creating a virtual environment. So you wear that big headsets that comes, on your eyes like goggles, and you're sitting in your maybe classroom, but you are feeling as though you're in Wonderla. That is virtual reality. So that's the feeling that people get. So if you look at this movie by Mr. Bean movie, there they showed virtual reality. Now, what is augmented reality? Augmented reality is you have a physical environment. On the physical environment, you augment image on top of the physical environment, and you're actually able to interact with that image. So in the industry 4.0, let us say that we have a physical room. In that room, I can create an image of a machine and then that image I can see it through my mobile phone or device and actually interact with it. That means I'm physically not touching the device, rather I'm moving my hand in the air, and in the air I can picturize image which has popped up, and I'm able to deal with it. Now I don't have to be in that room to do it. I can as well sit in my house and you know uh, project the setup of that machine in the factory using virtual reality and augment a device on top of it. Now, why is this useful? Because it basically helps me in understanding and setting up the situation, whether this new device fits in or how can this device be turned, rotated. So that is how augmented reality is used. Where augmented reality comes into picture in Industry 4.0 is I'm able to remotely monitor a machine in a factory by sitting at home. When I say remotely monitoring, it is not looking at the 2D image of the system of the machine. It is a 3D image that I am able to see, and whatever changes that I make to the 3D image, meaning to say rotate it or fix some parts and make some changes in real time, it gets connected with the machine which is there in the factory, and I'm able to remotely fine tune it. So that is where augmented reality comes into picture. There are a lot of videos on YouTube. Maybe I'll quickly do a search.
Yeah, thank you, ma'am. Thank you very much for your writing. Thank you very
Thank you,
much.
sir. You can go through, sir. You can type the keyword augmented reality industry 4.0 on YouTube, so you can
Okay.
see some examples. I'll also share some examples as part of my PPT. Some videos to give you an example of how augmented reality is used in industry 4.0.
Any other queries? Participants, any other questions? Ma'am, if no other question, can you wind up, madam?
Thank you so much. I would like to thank Shanmugesh sir and VJCET for providing this opportunity to me to deliver this session. I'm very thankful to all of you. I hope you enjoyed the session. Thank you so much. Have a nice day.
Thank you, madam. Let me invite Fenoske Francis for the vote of thanks.
Thank you, Jasma ma'am. Now we had a very informative section on artificial intelligence and machine learning. So I would like to thank Jasma ma'am for taking an informative section. Madam explained about artificial intelligence, agents in artificial intelligence, Industrial Revolution 4.0. She has also explained this Kaggle site and how to collect data from this Kaggle site. Then also collecting notebooks, data analysis, etc. in Kaggle sites. So thank you, ma'am, once again for this wonderful section. And thank you for all participants for your active participations in session 1, day 1. Thank you all. Thank you, one and all.
Thank you, one and all present here. So the chat box, we are given the feedback links. Kindly fill the feedback link